Thank you. And please keep me to task on the time because I think I've got too much here. So I may flip through some slides quickly. So I'm going to start by talking about who I am, but I don't think I have to now because you have. Talk about the ministry, their data strategy, and then how we applied this strategy. So I'm David Van Blankenstein. We can move on from that. They wanted to emphasize that I am contracted by MOTI. I'm not an employee. About the Ministry of Transport, there's some good details here, but I'm going to move through these two slides and talk to this next two sets to give people an idea of the scope of work that the Ministry of Transportation and Infrastructure has in British Columbia. British Columbia is a big, big province. It's a rocky province. We got a lot of water, a lot of islands, a lot of mountain passes, so they are very big. And for our Europeans, I've overlaid British Columbia in a different projection, of course, over England and Scotland and whatnot. So pretty much it goes from Paris to almost to Bergen. So it's a big piece of real estate. So they manage the highway system in British Columbia. I've put up an example here. This is the South Fraser Perimeter Road. It essentially connected Highway 1 to the ferry and the coal port. Took 2 or 3 years of planning and construction, but anybody who lives in that area knows what a relief it is to have that piece of road in place. What else do they do? Well, what could be more exciting than culverts? Culverts and guardrails and salt and reflective tape and power and water, everything you need to keep the mountain passes clear, the sea-to-sky highway going. And of course, less exciting is the planning, looking at where we are, what do we need to do to improve it, because we need to stay competitive in moving our goods to market, keeping traffic flowing on a big scale. So what's the spatial data strategy? It is basically, they have to focus as a ministry now on treating data as a valuable asset. So they want to, stage one, enhance its quality, then they want to be able to share it and use it. So it's a real motherhood statement. We've all seen this, organizations go through the transformation from caring about software and being indifferent to data to realizing that data is really the thing that's important. And also, as we will see, that location is key to pretty much everything that the Ministry of Transport does. Okay, so there you go, instantiating the strategy, like it's a big class. So the two main thrusts of the strategy are, let's improve the data, get the quality going. So I'm going to talk about how we have standardized the ministry on a single road base, because in the past there were multiple road bases. And then once we've done that integration, we're going to look at feeding information to a downstream automated permitting system for trucking. Okay, so standardizing the road base. It's pretty straightforward. There were multiple road bases forming, so they finally said enough. We've got to standardize on a single one, so they'll standardize on what is called the Integrated Transportation Network, which is maintained by GOBC. Single authoritative source. It's maintained by GOBC, but we have collaborations from the municipalities and the regional districts, the feds, because it's the road base in BC, it's all over the place. It's private, it's public, it's provincial, it's federal, it's local. It's evolving constantly. They're improving the geometry, they're improving the attributes on it, they're extending the attributes. And at the bottom, I just have a few notes on things that they have, like for demographic roads, they have the street ranges, lane counts. There's a bucket of data there. It's a nice, rich data set. This is my not particularly impressive graphic of what the road network looks like. Currently, to get a nice application to display it, it's too much data to bring up, so I just use the FME inspector and chop that. It's a lot denser than you, the public, would ever see, because this includes all the resource roads, so roads to logging camps and mines and whatnot. But it pretty much looks like the province. It's an ARC node network, like the prior talker would know about. So that's just a roundabout, And here's where we are in downtown Vancouver. We're by that green park there. And for more information, you can go have a look at their products and services. So, what was the integration? The integration, the ITN produces a product which is a denormalized geodatabase. We had a target data model in the Ministry of Transport, which was to essentially look after the business needs of the ministry. So we had to normalize the data model, and they threw the handcuffs on me right away. I could not go into an unconstrained database. So the database was developed and full constraints on. So there was a lot of blocked workspace runners. You had to load one piece before the next. You need the nodes before you can get the segments, and you put in the street names. Pretty much a meat and potatoes integration. I'm sure a lot of people here have experienced that. Here's the data model for reference. And well, a little bit of a sort of a hitch in it is that MOTI has a requirement that once they've stood this up, they want to be able to build the road base at any point in time. So fortunately for us, the ITN produces change logs. So we took the change logs in, do the standard history thing, process, deletes, inserts, updates. And one little problem we hit, which we'll talk about later, is that sometimes we rely on primary key chains to keep track of segments. Sometimes there would be a change that would mutate it, and we could no longer map to that subnetwork. But that's for later on. There's the obligatory workbench file. This is not a good one. I realized afterwards a standards person would club me to death, but they're not here, so I'm just going to move on and pretend that never went up. Now, the more exciting part of it is we've got the standardized road base. Now we need to support an application which is in the beta stage right now, which is automated routing and permitting, or en route BC. So essentially, in a nutshell, a truck driver wants to come in. I want to go from Fort St. John to Victoria. Give me a route. But this is not going to be a shortest distance route. We've got a bunch of things that we have to consider, which we will. So this is, I think this is actually a couple of years ago, but I'll pretend it was last year. 130,000 permits, trucking permits, and over half of them required you talking with someone and getting routing information around things based upon your load, primarily the weight of your load, the width of your load, and the height of your load. So here was the ask. The request is to associate restrictions, which I'll talk about, to the network, to define a backbone for trucks, and then output this representation to a proprietary application. So now we'll talk about restrictions. You can't emphasize how important restrictions are. There's something that, you know, I drive around in a truck, I don't have to worry about them, but the big rigs do need to worry about it. I was in Alberta about a year ago, and I had to get the family to stop on the highway because there was an overpass with a big bruise from a truck. Some truck came in there at great speed and hadn't done their checking and probably took the roof of their truck off. But this is a great picture because it demonstrates everything. It's width, it's height, it's weight, and it's clearly judgment too in this case. Okay, I think I've talked about that. There's three kinds of restrictions that the en route application is going to need to deal with. Static ones, which are bridges, underpasses, things like that. Dynamic restrictions, so there's a flood, or there's a fire, or there's a police event. So this will be fed into the system so you can update your route and avoid them. And then planned restrictions like parades, things like that. Construction, which we're all going to be enjoying in the next little while as the weather gets hot. So I'm just focusing on static restrictions. The other ones are looked after by the router. It's hard to describe. There are multiple units within the Ministry of Transport had been maintaining restrictions. Plus we had municipal restrictions and we had federal restrictions. So, and they came in a bucket of formats, text files, spreadsheets, geodatabases, you name it. So the thing was to bring them all in, and in some cases we had descriptions that we had to match to the road network. So there, cannot recall the transformer. I hope somebody remembers. Something like a fuzzy text matcher. And I use that a lot to match restrictions to roads. A lot of line joining, a lot of proximity searching. But at the end of the day, we managed to get everything in and matched. This is, if you're familiar with Vancouver, this is the Burnaby Lake area. What's sort of came out of the end of all the processing chain were these purple lines that represents segments in the road that have a restriction applied to them. And for the most part, this is all about height restrictions. So you're going to observe that, well, first of all, neither the restrictions nor the road network supports Z to any kind of level of detail. So how do you avoid a truck doing a left turn onto a highway when it's actually in the middle of an overpass? Because that, with a simple arc node topology, that if it doesn't know the altitude piece, it's doing a probably uncomfortable left turn to a 20-meter drop. So that's where we introduce the notion of what is called a Z level. And I'll just construct a small example here. This is the interchange of Pat Bay and Quadra Street in Victoria, where we're from. Actually, if you go into Google, you'll see that Google has it wrong. It puts the highway on top of the overpass. But so if we think of the roads as sort of bands or ribbons, they sit upon each other like that. And now the lower left, we have our simple arc node topology, which looks like we can now do this left turn onto the highway from an overpass. So we just do an encoding of Z levels. So essentially, you can turn at a node if where you're turning to has a common Z level. So in this simple case, the overpass goes from 0,1 to 1,1 and 1,0. It's really pretty simple. But if we just take something local to Vancouver here, just the south end of the Second Narrows Bridge, it starts to get a little more complicated. You got roads going under and over, and it's a little more tricky. And then if you go to a part of Los Angeles, it gets really tricky. But you can actually see kind of a symmetry in it. So I tried so hard to automate this. I thought I could automate this. I could take the network and I could figure out every Z crossing, and I just couldn't because it was structurally the breaks and the topology don't really reflect what's happening on the ground. So I took a couple of long evenings, a little bit of coffee, and I finally had to wave the flag. So now it became, what now FME was going to do was going to detect the problems, and we had to do a lot of squinting at it. But we did manage to cover the entire province. We had to bring in things like railways and pedestrian overpasses, pipeline right-of-ways and things, anything that a truck can smack into if it's too high. So I'm just going to do a little segue from here to a couple of problems that we solved along the way. This is one of my favorites. We had a lot of ferries in British Columbia. But when we first started this project, it was just a ferry route. So if you think about the way an arc node topology works, it's like, I'm going to take the shortest route I possibly can, but we got ferry routes that cross. So what was happening is I would be coming out of Tsawwassen, and then I turned left at Salt Spring, and because it was the shortest path, but you shouldn't be going there. So what we did was we just said, okay, we're going to build overpasses at sea. I'm going to use Z levels and build imaginary overpasses where the ferries cross each other. Because it was too dangerous to do underpasses at sea, but overpasses were okay. They were safe. You can get a sense of what's going on here. There's active pass, so they're all crossing. You got ridiculous routes happening. Now we've got a nice rich classification of the ferry routes. It doesn't happen anymore, but it was kind of fun at the time. And we're all data heads, so we know what fun is, real fun. Okay, a trucking backbone. So we don't want to be routing a truck from Chilliwack to North Vancouver and just go with the shortest path, because now you've got trucks going through neighborhoods and small roundabouts. Just lots of bad things would happen. So we have to define a backbone, and essentially the backbone is low cost. So the routing engine is going to get the truck onto the backbone as soon as possible, and then when it gets as close to its destination, then only then will it exit. Let's see. Okay, so I believe FME was involved here. Yes, of course it was. Well, this actually FME is involved everywhere here, because that's generally speaking the only thing I use. SQL and Python a little bit. So we got most of the way just by looking at the classification of the roads in the ITN, but we had data classification issues in that things like the last mile before a ferry terminal was given a low classification. So we wound up with a bunch of isolated networks. The backbone did not tie together. So you could not get to everywhere in the province if you hit that backbone. So that was a little bit more squinting, but we resolved it. So if we look at this next one, the green represents the backbone in the Burnaby Lakes area. And as another one of my cheesy diagrams with showing the province, so that dark blue line is the backbone and the fuzzy blue, baby blue one is just general roads. And then we get another segue. Segues are good. So what we have here is the ITN in totality is a bunch of isolated sub-networks. It just doesn't tie together for various physical reasons. A lot of it is islands that have no ferry service, areas where logging has occurred, but there's no road there. You have to get there by boat or plane. There's a funny little single segment road in the middle of a seniors care facility out by the university. I don't know. It's there. But it came out to 32,769 disjoint subnetworks in BC, which that's 16-bit integer minus 2. It's kind of profound. Or it's plus 2. Anyhow, I think I'll move on. That joke just failed. Moving on. All right. And if we just go back here, if you look up in the upper left, there are some pieces that we just can't tie in because actually connectivity comes through the Yukon. But that's okay. We just dragged in some road base from them and carried on. So the final product, we have the ITN in place. We've got Z levels. We've got a backbone defined. We still, however, have this outstanding issue where GeoBC will go in and correct a sub-network and it'll break all those key violations. There's really nothing we can do. It's just manual. Just get in and fix it. So long-term, that will be someone's monthly task is every time the ITN gets updated is do some good old-fashioned eye squinting. So the conclusion is it worked out really well. Now they are standard on a single base, and that's good. And they are able to support this routing application with a monthly update from GeoBC. And I think did I finish early? I have 2 more minutes. Well, we can have I think I've pretty much, not a lot of pointing back. Oh yeah. Go ahead.
Sounds good. Awesome. Well, thank you very much.
Thank you.
David, do we have any questions for David about the presentation? Yes,
Yes.
one over here. Great.
Is there any plans to have a 2-part question?
Okay.
I'm from TransLink. So
Okay.
are there any plans to expand the weight restrictions on the road to incorporate other types of vehicles like buses? And is there any plans with En route BC to incorporate a multimodal network, especially throughout the province?
The first one I think I can answer is that there was only so much I could do here. There's a lot of corridors that we had to define, just the same way as we defined the backbone. We had to define 40-ton corridors and 80-ton corridors, like special, like if a truck has to take something really, really heavy from here to there, you got to make sure that you're pretty careful with that, like exceptional roads or exceptional loads and things like that. So I would think that in time would also be incorporated into here, because once the definition of corridors starts happening, then it's just a question of adding a new corridor. So in that one example. The second one, I had to pull in the BC Rail, not BC Rail the company, but all of the rail in British Columbia as a separate piece when I was doing the restriction part. And there were some pieces of TransLink's, light rail system here that got pulled in. But I think that's probably long-term something that should be brought into place here.
Hi, Carlos from the airport.
Hey, Carlos.
I might have missed it, but what's the big difference between the ITN and the DRA?
The ITN is a lot richer. The DRA is really, it's a subset of the information. There's a lot of information in there that people don't want, the municipalities. It's like maybe the best thing isn't to say a simplified product, but it's a subset. The ITN itself is a lot richer. Like, I don't believe the DRA comes with a change log, for example. That would be one example. There's also attribution, which is not put out into the DRA, that is available through the ITN. So that would be the best way I would describe it.
Thank you. Any more questions? One over there.
So can you please expand on the vertical topology, how you built and maintained it?
When we first started, the ITN did not support topology, so we would use FME to build it. But it's essentially every segment knows the node that it goes to and the node that it comes from, so that gives us orientation. Now, a segment, so if we take a 4-lane road, if there's not a hard divide between it, a physical divide in it, it's modeled with one segment, which is oriented this way. So it carries a flag saying traffic can flow both ways, and also there's 2 lanes to the left and the right, respectively, of it. So otherwise, it's just essentially that relationship from the arc to the node. So the nodes have very little to do with it. It's mostly about the arcs, and that they know where they came from and where they're going to. Yeah. Now, the geometry in between is, I wouldn't say it's not relevant, but it doesn't change the topology. So you could have a road which did this, going from the node, and it can be abstracted to just be essentially a segment saying, from this node you can get to this node through this arc.
As long as someone brought us into the topological weeds, I was curious, the bridge example, and it's been a little while since I worked in this field, but the Z solution, the fact that you have nodes where you can't turn,
Correct.
is that a result of the way the network was generated, the software you're going towards, and did you consider having more of a network where arcs and nodes are only really where you can turn, and things, because I think what you have there is a node where you could have a weight restriction but having those restrictions more as events, bridges as events on the network, where your algorithm would work in a different way, where you don't actually have nodes where you can't turn.
Yeah, I was largely driven by the end product, which did the routing, and it's a relatively older product. So it's stuck in this world. But I think what you're talking about, sort of into the future, you would want to do it that way. I mean, the first step will be to solve the Z problem. Once I know that a bridge deck is 29 meters, and then I have a road that's 28 meters, and they meet, well, that's 1.2 meters clearance, so that's a bad example. We can limbo under it. That would be one way of automating it if I had that information. Another problem is that bridges typically, a road has width, and yet there's a single intersection point. And that's what was tricking my earlier attempt at an algorithm, was that there should be 2 breaks in it. There was no way to identify sort of the span of a structure to see what it affected. You know, I mean, I didn't talk too much about it here, but we had the whole problem of not determining the restrictions by mapping the structure to the network, but it was, so that broke the topology right there, because the bridge spans far beyond this one simple point. So you're right. There's a lot of different approaches that could be taken. In this one case, I was essentially driven by older technology.
Thank you. So there's time for one more question if anyone has. All right. Okay, we have one more. Okay.
What was
Well, I think for just raw frustration, it was the restrictions and the structures just coming from so many different systems. Some were descriptive, some were old road bases. But I really thought I could solve this Z problem. I looked at it, this is great. This is a topological problem. This is spent my whole life for the, getting to this point, and there's just sort of one night at midnight, I just said, I can't do this. I can't burn more effort on this. And then we went essentially what I call the quasi-manual way. FME will go out and it'll essentially give me a whole whack of places that I'm 99% sure this is a place where there's a crossing, and then it would diminish in value, and then we just basically had to hammer through it. It was, yeah. It basically collapsed into a data collection exercise.
Well, thank you very much, David.
Okay, thank you.